Combinatorial design theory is the part of combinatorial mathematics that deals with the existence, construction and properties of systems of finite sets whose arrangements satisfy generalized concepts of balance and/or symmetry. These concepts are not made precise so that a wide range of objects can be thought of as being under the same umbrella. At times this might involve the numerical sizes of set intersections as in block designs, while at other times it could involve the spatial arrangement of entries in an array as in Sudoku grids. Combinatorial design theory can be applied to the area of design of experiments. Some of the basic theory of combinatorial designs originated in the statistician Ronald Fisher's work on the design of biological experiments. Modern applications are also found in a wide gamut of areas including finite geometry, tournament scheduling, lotteries, mathematical biology, algorithm design and analysis, networking, group testing and cryptography. Example: given a certain number n of people, is it possible to assign them to sets so that each person is in at least one set? Each pair of people is in exactly one set together, every two sets have exactly one person in common, and no set contains everyone, all but one person, or exactly one person. The answer depends on n. This has a solution only if n has the form q2 plus q plus 1. It is less simple to prove that a solution exists if q is a prime power. It is conjectured that these are the only solutions. It has been further shown that if a solution exists for q congruent to 1 or 2 mod 4, then q is a sum of two square numbers. This last result, the Bruch-Reiser theorem, is proved by a combination of constructive methods based on finite fields and in application of quadratic forms. When such a structure does exist, it is called a finite projective plane, thus showing how finite geometry and combinatorics intersect. When q equals 2, the projective plane is called the Fano-plane. History: combinatorial designs date to antiquity, with the Loshu square being an early magic square. They developed along with the general growth of combinatorics from the 18th century. For example, with Latin squares in the 18th century and Steiner systems in the 19th century. Designs have also been popular in recreational mathematics, such as Kirkman's schoolgirl problem, and in practical problems, such as the scheduling of round-robin tournaments. In the 20th century, designs were applied to the design of experiments, notably Latin squares, finite geometry, and association schemes, yielding the field of algebraic statistics. Fundamental combinatorial designs. The classical core of the subject of combinatorial designs is built around balanced incomplete block designs, Hadamard matrices and Hadamard designs, symmetric BIBDs, Latin squares, resolvable BIBDs, difference sets, and pairwise balanced designs. Other combinatorial designs are related to or have been developed from the study of these fundamental ones. A balanced incomplete block design or BIBD is a collection B of B subsets of a finite set X of V elements, such that any element of X is contained in the same number R of blocks. Every block has the same number K of elements, and each pair of distinct elements appear together in the same number lambda of blocks. BIBDs are also known as two designs and are often denoted as two designs. As an example, when lambda equals 1 and b equals v, we have a projective plane. X is the point set of the plane and the blocks are the lines. A symmetric balanced incomplete block design or SBIBD is a BIBD in which v equals b. They are the single most important and well-studied subclass of BIBDs. Projective planes, biplanes and Hadamard 2 designs are all SBIBDs. They are of particular interest since they are the extremal examples of Fisher's inequality. A resolvable BIBD is a BIBD whose blocks can be partitioned into sets, each of which forms a partition of the point set of the BIBD. The set of parallel classes is called a resolution of the design. A solution of the famous 15 schoolgirl problem is a resolution of a BIBD with V equals 15, K equals 3 and lambda equals 1. A Latin rectangle is an R times N matrix that has the numbers chapter 1, 2, 3, n as its entries with no number occurring more than once in any row or column where Rn. An n times n Latin rectangle is called the Latin square. If r less than n, then it is possible to append n minus r rows to an r times n Latin rectangle to form a Latin square, using Hall's marriage theorem. Two Latin squares of order n are said to be orthogonal if the set of all ordered pairs consisting of the corresponding entries in the two squares has two distinct members. A set of Latin squares of the same order forms a set of mutually orthogonal Latin squares if every pair of Latin squares in the set are orthogonal. There can be at most n-1 squares in a set of MOLS of order n. A set of n-1 MOLS of order n can be used to construct a projective plane of order n. A different set is a subset D of a group G such that the order of G is V, the size of D is K, and every non-identity element of G can be expressed as a product D1 D2-1 of elements of D in exactly lambda ways. If D is a different set, and G in G, then GD equals GD. D in D is also a different set, and is called a translate of D. The set of all translates of a different set D forms a symmetric block design. In such a design there are V elements and V blocks. Each block of the design consists of K points. Each point is contained in K blocks. Any two blocks have exactly lambda elements in common and any 2 points appear together in lambda blocks. This SBIBD is called the development of D. In particular, if lambda equals 1, then the different set gives rise to a projective plane. An example of a different set in the group is the subset 1, 2, 4. The development of this difference set gives the Fano plane. An Hadamard matrix of order M is an M times M matrix H whose entries are plus or minus 1 such that H equals MIM, where H is the transpose of H and M is the M times M identity matrix. An Hadamard matrix can be put into standardized form where the first row and first column entries are all plus 1. If the order M greater than 2, then M must be a multiple of 4. Given an Hadamard matrix of order 4A in standardized form, remove the first row and first column and convert every minus 1 to a 0. The resulting 0 to 1 matrix M is the incidence matrix of a symmetric 2- design called an Hadamard 2 design. This construction is reversible, and the incidence matrix of a symmetric 2 design with these parameters can be used to form an Hadamard matrix of order 4A. When A equals 2 we obtain the, by now familiar, Fano plane as an Hadamard 2 design. A pairwise balanced design is a set X together with a family of subsets of X such that every pair of distinct elements of X is contained in exactly lambda subsets. The set X is allowed to be one of the subsets, and if all the subsets are copies of X, the PBD is called trivial. The size of X is V and the number of subsets in the family is B. Fisher's inequality holds for PBDs. For any non-trivial PBD, VB. This result also generalizes the famous Hurdos-de Bruijn theorem. For a PBD with lambda equals 1 having no blocks of size 1 or size V, VB, with equality if and only if the PBD is a projective plane or a near pencil. A wide assortment of other combinatorial designs. The Handbook of Combinatorial Designs has, amongst others, 65 chapters, each devoted to a combinatorial design other than those given above. A partial listing is given below. Association schemes. A balanced ternary design BTD is an arrangement of V elements into B multisets, each of cardinality K, satisfying. Each element appears R equals row 1 plus 2 row 2 times altogether, with multiplicity 1 in exactly row 1 blocks and multiplicity 2 in exactly row 2 blocks. Every pair of distinct elements appears lambda times, that is, if MVB is the multiplicity of the element V in block B, then for every pair of distinct elements V and W. For example, one of the only two non-isomorphic BTDs is the incidence matrix of a BTD can be used to form a ternary error-correcting code analogous to the way binary codes are formed from the incidence matrices of BIBDs. A balanced tournament design of order n is an arrangement of all the distinct unordered pairs of a 2n set V into an n times array such that every element of V appears precisely once in each column, and every element of V appears at most twice in each row. An example of a BTD is given by the columns of a BTD provide a 1 factorization of the complete graph on 2n vertices, k2n. BTDs can be used to schedule round-robin tournaments. The rows represent the locations, the columns the rounds of play, and the entries are the competing players or teams. Bent functions, Costas arrays, factorial designs. A frequency square is a higher-order generalization of a Latin square. Let S equals S1, S2, ed.m be a set of distinct symbols and a frequency vector of positive integers. A frequency square of order n is an n times n array in which each symbol C occurs lambda I times I equals 1, 2, m in each row and column. The order n equals lambda 1 plus lambda 2 plus lambda m. An F square is in standard form if in the first row and column all occurrences of C precede those of Sj whenever I less than j. A frequency square F1 of order n based on the set S1, S2, ed.m with frequency vector, and a frequency square F2, also of order n, based on the set T1, T2, Tk, with frequency vector are orthogonal if every ordered pair appears precisely lambda I mu j times when F1 and F2 are superimposed. Holt triple systems are Steiner triple systems with the property that the substructure generated by two intersecting lines is isomorphic to the finite affine plane AG. Any affine space AG gives an example of an HTS. Such an HTS is an affine HTS. Non-affine HTSs also exist. The number of points of an HTS is 3 meters for some integer m2. Non-affine HTSs exist for any m4 and do not exist for m equals 2 or 3. Every Steiner triple system is equivalent to a Steiner quasi-group Y equals X for all X and Y. A whole triple system is equivalent to a Steiner quasi-group which is distributive, that is, satisfies or equals for all A, X, Y in the quasi-group. Let S be a set of 2n elements. A Howell design H is an S times S array such that each cell of the array is either empty or contains an unordered pair from S. Each symbol occurs exactly once in each row and column of the array, and every unordered pair of symbols occurs in at most one cell of the array. An example of an H is a room square of side 2n-1, and thus the Howell designs generalize the concept of room squares. The pairs of symbols in the cells of a Howell design can be thought of as the edges of an S-regular graph on 2n vertices, called the underlying graph of the Howell design. Cyclic Howell designs are used as Howell movements in duplicate bridge tournaments. The rows of the design represent the rounds, the columns represent the boards, and the diagonals represent the tables. Linear spaces. An Lotto design is an n-set V of elements together with a set beta of k elements subsets of V, so that for any P subset P of V, there is a block B in beta for which PB, T, L denotes the smallest number of blocks in any Lotto design. The following is a Lotto design with the smallest possible number of blocks. 1, 2, 3, 4, 7, 1, 2, 5, 6, 7, 3, 4, 5, 6, 7. Lotto designs model any lottery that is run in the following way. Individuals purchase tickets consisting of k numbers chosen from a set of n numbers. At a certain point the sale of tickets is stopped and a set of p numbers is randomly selected from the n numbers. These are the winning numbers. If any sold ticket contains t or more of the winning numbers, a prize is given to the ticket holder. Larger prizes go to tickets with more matches. The value of L is of interest to both gamblers and researchers, as this is the smallest number of tickets that are needed to be purchased in order to guarantee a prize. The Hungarian lottery is a lotto design and it is known that L equals 100. Lotteries with parameters are also popular worldwide and it is known that L equals 19. In general though, these numbers are hard to calculate and remain unknown. A geometric construction of one such design is given in Transylvanian lottery. Magic squares. A Mendelssohn design, or MD, is a V set V and a collection beta of ordered k tuples of distinct elements of V, such that each ordered pair with xy of elements of V is cyclically adjacent in lambda blocks. The ordered pair of distinct elements is cyclically adjacent in a block if the elements appear in the block as or. An MD is a Mendelssohn triple system, MTS. An example of an MTS on V equals 0, 1, 2, 3 is. Any triple system can be made into a Mendelssohn triple system by replacing the unordered triple A, B, C with the pair of ordered triples N. But as the example shows, the converse of this statement is not true. If is an idempotent semi-symmetric quasi-group, that is, x equals x and x equals y for all x, y and q, let beta equals x, y and q, then is a Mendelssohn triple system MTS. This construction is reversible. Orthogonal arrays. A quasi-3 design is a symmetric design in which each triple of blocks intersect in either x or y points. For fixed x and y called the triple intersection numbers. A symmetric design with lambda 2 is a quasi-3 design with x equals 0 and y equals 1. The point hyperplane design of PG is a quasi-3 design with x equals, and y equals lambda equals. If y equals lambda for a quasi-3 design, the design is isomorphic to PG or a projective plane. A T-design D is quasi-symmetric with intersection numbers x and y if every two distinct blocks intersect in either x or y points. These designs naturally arise in the investigation of the duals of designs with lambda equals 1. A non-symmetric 2 design is quasi-symmetric with x equals 0 and y equals 1. A multiple of a symmetric 2 design is quasi-symmetric with x equals lambda and y equals k. Hadamard 3 designs are quasi-symmetric. Every quasi-symmetric block design gives rise to a strongly regular graph, but not all SRGs arise in this way. The incidence matrix of a quasi-symmetric 2 design with kxy generates a binary self-orthogonal code. Room squares. A spherical design is a finite set x of points in a dimensional sphere such that, for some integer t, the average value on x of every polynomial of total degree at most t is equal to the average value of f on the whole sphere, i.e., the integral of f divided by the area of the sphere. To run systems. An R times n Tuscan K rectangle on n symbols has R rows and n columns such that each row is a permutation of the n symbols n. For any two distinct symbols R and B and for each m from 1 to k, there is at most one row in which B is m steps to the right of A. If R equals n and k equals 1, these are referred to as Tuscan squares, while if R equals n and k equals n1, they are Florentine squares. A Roman square is a Tuscan square which is also a Latin square. A Vatican square is a Florentine square which is also a Latin square. The following example is a Tuscan 1 square on 7 symbols which is not Tuscan 2. A Tuscan square on n symbols is equivalent to a decomposition of the complete graph with n vertices into n Hamiltonian directed paths. In a sequence of visual impressions, one flashcard may have some effect on the impression given by the next. This bias can be cancelled by using n sequences corresponding to the rows of an n times n Tuscan 1 square. A T-wise balanced design of type T- is a V set X together with a family of subsets of X whose sizes are in the set K, such that every T subset of distinct elements of X is contained in exactly lambda blocks. If K is a set of positive integers strictly between T and V, then the TBD is proper. If all the K subsets of X for some K are blocks, the TBD is a trivial design. Notice that in the following example of a 3, 12, 4, 6, 1 design based on the set X equals 1, 2, 12, some pairs appear 4 times while others appear 5 times. 1, 2, 3, 4, 5, 6, 1, 2, 7, 8, 1, 2, 9, 1, 1, 1, 2, 1, 0, 1, 2, 3, 5, 7, 8, 3, 5, 9, 1, 1, 3, 5, 1, 0, 1, 2, 4, 6, 7, 8, 4, 6, 9, 1, 1, 4, 6, 1, 0, 1, 2, 7, 8, 9. 1, 0, 1, 1, 1, 2, 2, 3, 8, 9, 2, 3, 1, 0, 7, 2, 3, 1, 1, 1, 2, 4, 1, 8, 9, 4, 1, 1, 0, 7, 4, 1, 1, 1, 1, 2, 5, 6, 8, 9, 5, 6, 1, 0, 7, 5, 6, 1, 1, 1, 2. 3, 4, 9, 1, 0, 3, 4, 1, 1, 8, 3, 4, 7, 1, 2, 5, 2, 9, 1, 0, 5, 2, 1, 1, 8, 5, 2, 7, 1, 2, 1, 6, 9, 1, 0, 1, 6, 1, 1, 8, 1, 6, 7, 1, 2. 4, 5, 1, 0, 1, 1, 4, 5, 7, 9, 4, 5, 8, 1, 2, 1, 3, 1, 0, 1, 1, 1, 3, 7, 9, 1, 3, 8, 1, 2, 2, 6, 1, 0, 1, 1, 2, 6, 7, 9, 2, 6, 8, 1, 2. 5, 1, 1, 1, 7, 5, 1, 8, 1, 0, 5, 1, 9, 1, 2, 2, 4, 1, 1, 7, 2, 4, 8, 1, 0, 2, 4, 9, 1, 2, 3, 6, 1, 1, 7, 3, 6, 8, 1, 0, 3, 6, 9, 1, 2. A Euclidean square is a K times V rectangular array of E symbols such that each symbol appears exactly once in each row and the symbols appearing in any column form a block of a symmetric design, all the blocks of which occur in this manner. A Euclidean square is a Latin rectangle. The term square in the name comes from an older definition which did use a square array. An example of a 4 times 7 Euclidean square is given by the 7 blocks form the order 2 biplane design.